Okay. Let's look at another message type next. Called TCNBPDU. Then before you talk, I will draw a topological map. Let's see if it's necessary. Let's talk about the environment first. As long as you understand the environment, this message is easy to understand. I now draw 3 devices first. Still connecting the cable. Then after our choice. Finally, this port was elected as a blocking port. That is, this port does not perform traffic forwarding on a daily basis. Let's give them a name first. There are 3 devices in total. The one on the left is still device A. On the right is still device B. This is device C. Only these devices will not work. I still have to draw 2 PCs. Suppose a PC is connected under one end. Draw another PC here. We now assign 2 interfaces to device C. For example, this interface is C1. This interface is C2. The same is true for device A. This interface is A1. This interface is A2. Device B is not needed here. Assuming the device on the left is not a PC. It is a server. On the right this is a normal user's PC. That is, there is such a server in the intranet. After we network based on the switch. I hope this PC can access this server every day. For example, here are some OA systems of the company. So, now I want to access it daily. Then the way must be passable. Once we have communicated the data, send this data here. Finally, send data packets and reply data packets. Then everyone should know. There will be a MAC address table on both devices. Suppose now a MAC address table of device C. As such a device, it must have its own interface. Suppose the interface is C1. C1 corresponds to an address that is the address of the PC. I actually told everyone. When the data is being encapsulated as a whole. In fact, the interface of the switch does not have a MAC. So now send the data here. From the C1 this learn the MAC from the PC. Then the final data if the past. Reply packet. Remember ARP? Send a broadcast message. Then all devices that receive have a reply. For example, PC wants to request server. The IP address of the PC is 1.1. It is 1.2. It needs reply packets. If the message replied by server passes through the C2 interface, then C2 will learn server's MAC. That is, the address corresponding to the C2 interface is the MAC of server. Here is the MAC address table for device C. Same. Let's take a look at the MAC address table of device A. For device A. Now under the A1 interface. This must be a PC. This is the server under the A2 interface. When it receives data now. Messages received from PCs here. A1 corresponds to PC. If the future server replies to the packet, return to device A from A2 interface. This A2 interface is learned here is server. So now you will find. Every day when we communicate. This is how the PC accesses the server. Because now the data has arrived. We need to look up the table. Check the table here. This is requested through ARP. The sent message can be learned by the devices along the way. The MAC address table was built successfully. Then it goes to the server and sends it from interface 2. Then send it. Device B will not be discussed. Because it has nothing to do with it. Let's discuss a scenario. When one day the line between device A and device B is broken. Then the blocked port on device C will become a designated port. The direct link is down now. For device C. It is indirect. It is this picture. But we are not discussing this picture. We don't discuss forwarding time. It stands to reason. This interface should start data forwarding. Assuming that the 50 seconds have now passed. It has become the state of forwarding. So do you think there is any problem with this forwarding process? Now the line is broken. Let's see how it is forwarded. As a switch. The PC still accesses the server. Data arrives at the switch. The switch needs to check its own MAC address table. Then the server is on its number 2 interface. It corresponds to send out from here. The data still arrives at device A. Device A table lookup. Send from its port 2. After sending out. Found a problem with this line. There is no way for this message to reach the server. Some friends may find it strange. Now this interface forwards. Shouldn't the data go like this? How could it go up there? We have a question. The data arrives at the switch here. The PC is only responsible for sending the data. The switch forwards based on the appearance lookup table. In the MAC address table. It is going to server now. Server corresponds to C2. It will only be sent from C2. If this interface is C3. It hopes to send from here. Because it forwarded. But the switch knows the link is down now. That is. The MAC address table in the switch does not care about these. For the MAC address table. Both interfaces C1 and C2 are working normally. This interface is not down. Then this appearance exists. And the aging time of the MAC address table is 300 seconds. For switches. 300 seconds is 5 minutes. The MAC address table has always existed. Under what circumstances can it find that we should switch links? There is a situation. Wait 5 minutes. After the appearance of the server. Through the C2 interface naturally ages. Let's ping again. It will resend the broadcast to request. And the embarrassing place is. The other party is a server. It will not actively send data packets. It's okay if the other party is a PC. Because if the PC communicates. If this link is broken. It must send ARP. After making an ARP request. Data will come from here. If the data of server comes from here. Suppose this interface is C3. You will map such a MAC to C3. Because one MAC address cannot correspond to 2 interfaces. It originally corresponds to C2. But it received from C3. It will refresh the address table. But unfortunately. Its peer is a server. The server will not actively send data packets. It can only wait for passive access. That is. Such a representation will not be refreshed. A PC can only wait for it to age naturally. When it gets old. The PC needs to request the MAC address of the server again. The ARP aging time on the PC side is relatively long. 20 minutes. But its data goes to the switch. This is an unknown unicast data frame to the switch. The switch needs to perform flooding. Then this data will be sent from this interface. Will be sent from this interface. But this interface does not work here. So the switch cannot learn server from C2. Send it here. The server will reply a data packet to it from the C3 interface. So now device C can update its appearance. It turns out that this server corresponds to the C3 interface. Once the MAC address table is updated now. This PC then visits the server. The switch knows that it should be forwarded from this interface. Will be sent. So wait at least 5 minutes for this time. For the current business flow. STP is to quickly complete the switch. Stop talking 50 seconds now. It's 30 seconds. The environment can't afford to wait now. If it really takes 5 minutes to switch. No one will use this agreement. If the link fails now. Our current projects will combine traffic monitoring. 5 minutes is enough time for me to call the police. Then I rush to the computer room to see the configuration. Too long. So this is definitely not optimized. So the reason why this happens. Because our collective information. No way to get timely updates. This link is now in forwarding state. But the device itself doesn't seem to know. That's why messages like TCN-BPDU appear. Okay. Our next picture. I will draw more pictures today. I draw a better understanding. For example. Now here are some devices. For these devices. For example. Now this device is originally connected to other. But at some point one of its ports becomes forwarding state. Then it has to tell other devices. It is now switching state. If the interface is now in the forwarding state, then please pay attention. Will be controlled by the root port on this device. Send a BPDU message upstream. Called TCN-BPDU. It is a topology change BPDU message. Will be sent by the RP port of the device. Send this message to the upstream device. Tell it. The interface of a device below is now forwarding. So it will send this message to the upstream. I will simply draw its process. When the above device is received, it will be from its own designated port. Send a BPDU message to the downstream device. Because the daily designated port sends BPDU out. Usually this is the designated port. Below are the root ports. It sends configuration BPDU. But what is different in the configuration BPDU? It's in flags. There is a man named TCA. It will set this bit to 1. Originally this bit was 0. But it sends a set bit to 1. This message means topology change confirmation. Means it's off now. It is replying this confirmation to the downstream device. Then it will continue to send TCN-BPDU up. Tell the device above. Now the device below has changed. I draw shorter. This goes straight to the root. If it is not root, the upstream device will then send a configuration BPDU to the device. Tell it to stop. Then it goes up. Keep sending it until it reaches the root bridge. After the root bridge receives, it sends a configuration BPDU. Among them, except TCA is set to 1 in flags. It will also set another TC to 1. TCA is set to 1 to tell the device not to send. Secondly, it sets TC to 1 at the same time. The representative tells the entire network to refresh the MAC address table now. It is equivalent to replying to a message. Sent a message. But did 2 things. TCA is to tell the lower equipment not to send. Secondly, the TC will always forward the message downwards. Because this is a configuration BPDU. Other devices are to forward the configuration BPDU of the root bridge. The meaning of this TC setting is: tell all devices it's time to update their MAC address tables. Then all devices will clear their MAC address table. Relearn. It is equivalent to the fact that there is a server corresponding to C2 in the device. As a result, it is sent from C2 every time it goes to server. For now, these MAC address tables are emptied directly. Then any data sent by the PC now. It is an unknown unicast to the switch. All switches must perform flooding. As long as the switch performs flooding, then it will learn the correct server MAC. Then put it in your address table. So the process is very fast. That is, we manually cleared the old one that should have been. As long as there is such an interface in the environment. From the original blocking to forwarding. It means that the topology of the entire network must have changed. There must be an interface state change. That means The things stored in the MAC address table in some devices are wrong. So be conservative. Everyone started to refresh the MAC address table. Then relearn. That's what I mean. This message has a sending time. It will send a total of 35 seconds. The first time you start sending down. Send once in 2 seconds. Send in 35 seconds. Then stop. Keep sending. Until it is confirmed that all devices on the entire network receive this message. Configuration BPDU and TCN BPDU are two packet types. How to distinguish? Distinguish in BPDU type. One is configuration. One is TCN. TCN is dedicated to the interface below to become forwarding. Reported upwards. Then the reply is always the configuration BPDU. It's just that it will modify the parameters of the two flags inside. Then send down. TCA means it knows and don't send it. TCA represents the entire network to refresh the MAC address table. Okay. Then we basically talk about STP is almost the same. Now for STP. It also doesn't have much configuration to speak of. It is more about some understanding of the entire agreement. Very theoretical in the NA stage. When you reach the NP stage in the future, you will learn a lot about some protection mechanisms of BPDU. Include some switching mechanisms. There will be many experiments. Let's talk about DHCP and CDP next. DHCP is called Dynamic Host Configuration Protocol. That is, you can configure some address parameters for it without static manual configuration. When we run the DHCP protocol in the network in the future, I can make some terminal devices automatically obtain some online parameters. For example, I want an IP address. We need to manually configure. I want a gateway. We also need to manually configure. I want to write a mask. Also requires manual configuration. In the future, use this device to access some domain names on the public network. I have to request its IP. So how do I know its IP? DNS is also configured. These parameters are when we go online normally. Some parameters to assign. Then let's take a look. For me now. Look at my network card. There will be a DHCP enabled. Indicates that the device is now enabled with DHCP. There are a few things in here. One is called an IPv4 address, a subnet mask, a default gateway, a DNS server. These are the four more important parameters. It is the core content of our explanation today. When we talked about the reference model earlier, there is a protocol stack. Now if this device wants to complete the communication normally, in fact, we open the protocol stack of TCP IPv4. This is the system comes with. But you will find, when I am getting parameters online now, what is actually used is to automatically obtain. In fact, it is DHCP. Then we can also change it to use the following IP value. Manual configuration. So if we want to specify the device, to configure the following parameters: IP address, mask, gateway, and DNS server. So these parameters are actually. Now a computer must need some parameters when it wants to complete the communication normally. Let's recap. What is the role of these parameters respectively? First of all, the IP address is the identifier of a device. Network communication uniquely identifies the logical address of a device. What does mask mean? An IP address plus a subnet mask. You can confirm which network segment the device belongs to now. Direct communication on the same network segment. Communication between different network segments requires a gateway. For example, this is a router. This is an interface. This is a gateway. This is a PC. Then PC will communicate across network segments in the future. It's going to request the gateway's MAC. Then the gateway must be on the same network segment as it. That is, it belongs to an address of the internal network port. These are the knowledge we talked about before. Our daily internet access must cross network segments. So these parameters have. We will not learn too much about this DNS. For example, internally some devices to access Google. This has a router as an egress. Then make some connections below. This router is connected to the operator. Suppose the operator is connected to a Google server. Suppose the address of Google server is 123.1.1.1. But when we actually go to Google, in fact, it is not directly sent a data. Source IP is 192.168.1.10. The destination IP is 123.1.1.1. Not a direct encapsulation. Find it directly. But across the public network, there will be other devices designed to help us do other things. This device is called a DNS server. This server will store a lot of correspondence between domain names and IP addresses. For example, www.google.com. Its corresponding address is 123.1.1.1. Normally, when you visit Google, more domains that visit Google. For example, ping www.google.com. Ping is a domain name. But logically, communication should be based on an address. Can't communicate with a domain name. Actually, before you go to actually access the Google server now, we'll first send a message. The destination of this message will be the DNS server you configured. The message content is the IP address corresponding to www.google.com. You would send a packet asking. It receives the message and retrieves it locally. After that, it will reply you with a message corresponding to this message. It will give you the corresponding response. So now the host gets www.google.com corresponds to 123.1.1.1. Then you go to data encapsulation. Only then will the destination IP be written as 123.1.1.1, which is equivalent to. You will send this message to 123.1.1.1. Instead of sending directly to 123. 1.1.1. But for us, this thing has no perception and we're done. But you need to know. We will have a server like this. Actually, we all need to configure the host. But we don't seem to have configured the internet now. Because what we are actually using now is the way of automatic acquisition. DHCP is a must. It's not just a matter of cumbersomeness. Manual configuration has some disadvantages. For example, I am now going to configure an address for my computer. I choose manual configuration. First of all, manual configuration is a lot of work. You can easily configure address conflicts. For example, you are now operating a network. There may be hundreds of devices in this network. You need to plan the network segment. You also have to remember who used each previously assigned address. You can't assign duplicates anymore. Otherwise, address conflict. It's easy to go wrong. It can be avoided. But there is one circumstance that cannot be avoided. Or you can't use manual configuration. That is, when you are in a public place. There is no way to configure it manually. If you go to a coffee shop and have a cup of coffee, you can't tell the clerk. Connect to their Wi-Fi. Let them assign you an IP. This is impossible. If you want to connect to the network inside the coffee shop, surf the web through their devices, you need to configure an IP. Then this IP needs to be on the same network segment as the internal configuration of the coffee shop. Just find the gateway. At least there must be parameters in the Internet address configuration. If we all use manual configuration now, then the Internet will be very inconvenient. So there are some scenarios where there is no way to manually configure, because this function has a relatively certain threshold, and it's too much trouble. So we now use more dynamic configuration. Dynamic configuration is what we call DHCP today. Dynamic configuration requires running DHCP between the server and the client. It's easy for the client. You don't need to type the command. The client is a graphical interface. You just need to click this directly to run the protocol. But the router side needs to be configured. Then let them be based on the DHCP protocol. Automatically send some address parameters to the host. This DHCP server does not need to purchase the hardware of the DHCP server separately. For example, it can use a router, layer 3 switch, firewall. This can be simulated. They can simulate a DHCP server like this. That is, DHCP server configuration can be done directly on other devices. You don't need to buy a separate server. Let's take a look at how DHCP works. Look at this picture. There are two devices. The device requests an address from a server. Then assign the address. Okay. Let's look at the message type next. This is a topology. Let's wait for the configuration. It will be configured as a DHCP server. Next, here are the two devices. This is the client. It is a very standard CS architecture. It's a client-server architecture. The client asks the server for some services. The server provides corresponding services to the client. This is called the CS architecture. In this schema type, we need to know how DHCP works. Then we need to know which messages DHCP will send. Let's just look at the first four. We don't really need the latter two during the request phase. For messages, let's take a closer look at the sending rules. First of all, here is a DHCP discover. This is called the seek message. When the client looks for the server, first it sends the message. Since it wants to find this server, definitely send packets. If you send a data packet, you must perform data encapsulation. If you want to package. So how to encapsulate the source IP and destination IP? This is the only interesting thing in the boring configuration in DHCP. Now there is no IP to request IP. That must have no source IP. But if you don't fill in the source IP, can't send packets again. When we talked about IP addresses earlier, speaking of some special IP addresses, for example 40, in addition to representing any address on the entire network, make a default root other than. It can actually represent the unknown. Represents no IP now. The destination IP is called the network-wide broadcast address. Is also a restricted broadcast address. 4255. Binary is all 1. For 255 reps. Now all devices only need to receive this message. Must be processed. This is called the network-wide broadcast address. So the first message sent by PC1. That is, this DHCP discover is such a message. The second layer is packaged like this. Then once the message is sent, the switch only needs to be powered on. Then both PC4 and R1 will receive. After receiving R1, found that a device is asking it for an address. It is a server. Then it has to reply to the address. It provides this service. When R1 replies to it, It is necessary to reply to it with a second message type, called DHCP offer. There will be some parameters in the reply message. It will carry what address it wants to assign to this device. And I want to emphasize to you a question. When the PC sends a message, the second layer of encapsulation source MAC must be itself. The purpose MAC must be all one. Actually, when the server receives this message, it is able to learn this PC's MACs. So, when the server replies to the packet, in fact, it can be unicast back and forth. Because as a PC, it will look at the second floor first, then look at the third floor. It can directly turn the destination IP into a unicast inside Cisco when it responds to an offer broadcast. Although it can learn the MAC address of PC3, but it doesn't. It will send a broadcast. Then both devices can receive. Certainly. Because for the device is the request made by PC3. So PC3 will receive. PC4 is not requesting now. So it's not replying to what you sent. Just know the way. This is called a DHCP offer. It will be carried in the offer. What address do you want this device to use? For example, you have planned some addresses here. Used it. Then when it received, it will reply again. It will reply a request. In this request message, will carry some address it now wants to use, including the server it chooses. Some students may ask, what is the selected server? Isn't this just a server? Sometimes we are in some network environments. There may be multiple servers. It's a backup problem. For example, now there are a lot of devices in the network. I just point to a server to assign me an address. One day it suddenly went down. Now what about the addresses below? So often there may be multiple servers in an environment. If there are multiple servers, it will face a problem. When the PC sends a broadcast packet to find the address, both servers will receive. Then as long as server receives it, it will reply. Now the address that the PC replies to is not the same. This PC is about to choose whether to use device 1 or device 2 as your own server. And what exactly is the address given to you by device 1? Or the address given to you by device 2? So in this DHCP request, we'll carry the address you want to use, and the server you want to choose. And the packet you sent is a broadcast packet. Suppose now you want to select device 1. It assigns you an address of 1.1. Device 2 assigns you an address of 3.1. It is also possible that it is not on the same network segment. For now, you send a broadcast packet. It will carry that you want R1 to be your server, and you want to use the address 1.1. You send it as a broadcast on behalf of. Both devices can receive. Then device 1 knows to use its address. It will give you an ACK. Make a response to this message. And is locally documented. Why send it to this device? Because it is broadcast. So R2 can also receive. R2 received and found that the choice is R1. It takes back the allocated address. For other clients in the future, this broadcast message not only told the server you want to choose. Let the server you don't want to choose know that you are not selected. So this is a very optimized mechanism. Sending a broadcast is equivalent to telling everyone. To us. Here is a bogus DHCP attack. When you reach the NP stage in the future, you will learn DHCP snooping. Then you will solve it. For example, some devices are privately connected to the network. Privately entered a DHCP server. Or privately came in a TP-Link. Because TP-Link opens some DHCP functions by default. If the TP link is privately connected in the internet, it may cause your device to be unable to connect to the internet now. When you send a message, maybe it replied to you first. We didn't say who it would choose. This is very simple. It receives the message from who sent it first. Whoever it chooses. Device 1 first sends it. It selects device 1. Device 2 first sends it. It selects device 2. Finally, the client sends a confirmation to it. Then this address is used for it. The local will remember which MAC this address is used for. After that, it will not redistribute this address to other devices. Here are some conceptual parts. Let's look at the configuration next. The configuration is also very simple. Throughout the NA phase, many things are actually a basic understanding. So it's not hard to configure something. We first turn on these devices. Some students may ask, under what circumstances will the client reject the offer? The client has a release address. You can release it manually, but it won't refuse, because this service is initiated by it. Suppose it now initiates a message. Want an address. The device gives it an address. Then it refuses. This situation does not exist. Only two cases. One is that it is going offline. The second is that it wants to configure manually. Then it will actively send messages to the device. Release the address allocated by the device. It will not take the initiative to reject the offer. If it now receives two messages at the same time, then it will choose the first, not the second. Because there is no need. Unless there is an artificial configuration. It doesn't want to use DHCP anymore. It will release this address.